All right. Hi, everyone. Welcome to week 4 of Math 2504. So because of the public holiday on Wednesday this week, a couple of us tutors are just going to be creating this video to run through the practical this week, which is practical C. So we're just going to be doing, working through some basic Unix commands, showing you how to use Git and GitHub, and some basic IDE usage, so VS Code in particular. And just before you get started on the prac, make sure you've done all of these things. So make sure you set up your GitHub account, the SSH connection to GitHub. If you're on Windows, you'll want to have Git Bash installed. If you're on Mac or Linux, you'll want to have Git installed. And the IDE that we recommend is VS Code. So grab that as well. And you'll want to install the Julia for VS Code extension. Cool. So we'll just get started. So first off, we're going to work through some basic Unix commands. So start by opening your terminal. If you're on Mac or Linux, this should already come pre-installed. If you're on Windows, you'll need to get Git Bash. So when you first open up your terminal, you will be in the home directory, which is represented by this little tilde here. If you're not in your home directory for some reason, you can get to it using cd tilde. So cd stands for change directory, and the tilde is just the location that you want to go. If you just type in cd, by default, that will take you to your home directory as well. And now we want to make a directory called prac_c_work. And the way we do that is with make_dir. So make_dir stands for make directory. So if you do make_dir prac_c_work, we can then go into that directory using cd again. And you'll see that this path should update here as well. So now we're in the prac_c directory, which is a directory that lives inside our home directory. Right. Now we want to make a parent directory. So you want to make a directory in here called Australia. And inside we'll have a couple more directories, one for each of the states. And it says try to create each of these directories with 2 make_dir commands. And one way we can do that is like so. So we've already created the Australia directory. Now to create each of the subdirectories, we can do something like this. So everything inside the braces, each of these fields, each of these comma separated fields will sort of expand out into its own separate command. So this is basically just a shortcut for running like make_dir Australia / New South Wales, and then Queensland, NT, and so on. So if we just run this, so it'll give me an error there because I've already made these 3, but that should be okay. So now what we can do is we can cd into Australia. And then if we do, to list the contents of a directory, we use ls. And you'll see that we've got all of these subdirectories living inside Australia now. All right. Now we want to create 6 files, each named capital.txt, living inside the respective subdirectory of the state. So one way to do this is to do it just on the terminal, and we can use the echo command for this. So we can echo, for example, Brisbane into, so we're already in the Australia directory. So let me just hop back out actually. So cd ... is the parent directory. So cd ... basically means go back a directory. You'll see we've jumped back to prac_c_work. Now we can, for example, create the capital.txt file in Australia/QLD by doing this. So Australia, QLD, and then the file name. Right. Now, one way we can check that it actually did what we want is with cat. So cat is a command that will print out the contents of a file. So if we cat Australia/QLD/capital.txt, that gives us back Brisbane as expected. We can also ls Australia/QLD to look inside the contents of this directory, and we'll see that we have capital.txt as expected. So that's how you do it on the terminal. If you prefer, we can also do this in VS Code. So if you already have VS Code installed and set up, what you can do is type in code and then dot. So code takes an argument, or the first argument that it takes is the directory that you want to open up VS Code in. Dot stands for the current directory. So what this means is it will open up VS Code and set your workspace to be the current directory. So when we open up VS Code, it'll pop us in this prac.c work directory. Oh, and you can see up here, it says prac.c work, and we have this Australia directory that we just created. And if we expand that out, we'll have all of the other subdirectories that we created as well. So in Queensland, this is the capital. So the capital text file that we created. And we can do the same thing here and create text files for all of the other states using VS Code. So if you tap this, so if you click on this button here on the very left, new file, you can create a text file just as you would. So let me just go through and create all of these text files. One thing I didn't mention is that when you create a new file and you start typing in it, you'll see at the top here that you have this white circle. So that means that there are unsaved changes. And then if you do Control S to save, you'll notice that that dot turns into an X, and it just means that that's been saved. So we can now safely close all of these. Now, if we hop back to the terminal, we can check that all of these have been created as well. So we can do ls Australia slash and then QLD, for example, or we can do NSW, and we can check through all of them. Now, a quicker way of doing this is to use -r. So -r is an option that you can pass to ls. And R stands for recursive, and we are going to look inside not only this directory, but all of these subdirectories as well. So if we run ls-r in this prac.c work directory, so remember dot stands for the current directory. So in the current directory, we have Australia. And then inside Australia, we have all of these states, these subdirectories that we created. And ls-r will just output all of the files that are in each of those subdirectories as well. So this is handy if you've got a file structure like this, where you've got a lot of directories that you need to look in. There are also a couple of other flags you can use that are mentioned here. So if you do ls-l, that will list, if you do ls-l, it will list all of the items in your directory each on their own line, and it gives you a bit more information as well. So you have like the timestamp, the owner of the file, some permissions as well. If you do ls -a, it reveals hidden files and hidden folders as well. So in Unix systems, a file or a folder that starts with a dot is considered a hidden file, and you won't be able to see those with ls. So to see those, we run ls -a, and you can see these two additional entries pop up. So these just stand for the current directory and the parent directory, respectively. You can also combine these flags. So for example, we could do ls -al, or la will give us the same thing. We can add r as well to get a recursive listing, like so. Cool. Right, now go into the ACT directory. And we want to use pwd. So pwd stands for print working directory. And it gives you the full absolute path of this directory. So you can see here that my home directory is actually /home/ my name. And then this part here is everything that comes after. So if you go back to your home directory, for example, and you run print working directory, this will give you the absolute path for your home directory. So you can see that tilde is just sort of like a shortcut or an alias for this path here. So going back to the ACT directory, we've got a couple things to do. And the challenge here is that we need to do them without leaving this directory. So the first thing is we want to remove the capital file in the Queensland directory using an absolute path. So an absolute path is basically something that looks like this. So we're beginning from / and we're listing out the directory or the path in full. So the way you would do this is rm and then list out the entire path to your directory. So prac cwork Australia qld capital.txt, and rm is the command to remove a file. Cool. And just when you're doing these as well, you can use VS Code or a file explorer as well to sort of confirm that your commands have been successful. So you can see here that the QLD folder is now empty because we just removed the capital.txt file. All right, now we want to remove the capital file in the New South Wales directory, but this time we want to use a relative path. So relative path is basically like what it says, it's relative. So it's relative to your current directory. And the way we do it, the way we sort of reason about that is we use the dot and the dot dot. So dot for current directory and dot dot for the parent directory. So to get to the New South Wales directory, we first do dot dot to get back to the parent directory, which is Australia. And now we go into the New South Wales directory using /nsw and then capital.txt. We can then check again in VS Code that folder is now empty as well. Something else we can do is rename a file. So the command to do this is mv. And actually mv can do two things. It can move a file and it can change the name of a file. So using a relative path, we can get to this file like so. So sa/capital.txt. So the first argument that you pass to mv is the source, so the file that you want to move or rename, and then space, and then the path. Sorry, the second argument is the destination, so what you want to rename the file to, or where you want to move it. So in this case, if we keep it in the same directory, so /sa, but just change the name of the file like that, this will essentially just rename the file because we're not moving it to any other directory, but we're changing the name of the file. And if you go to VS Code and just confirm, we now have this file with a capital C in the SA subdirectory. All right. Another thing we can do is append lines to an existing file. So using a relative path, we can echo is very far west to so /wa/capital.txt. Now, if we check that file, you'll see that that file has been modified. All right, cool. So I believe that's all for that one. All right, now we go back to the home directory. Again, we can just use CD to do that. And now to copy files, we can use CP. So copy CP, like MV, takes 2 arguments. So the first argument is where you're copying it from, and the second argument is where you're copying it to. So we're copying from /cwork/Australia /WA/capital, and we're just copying it into the current directory. So that's just going to be dot. And again, we can confirm with ls. I've got a bunch of other things in here, but you can see that capital.txt has been copied over. And if we catch capital.txt, we can see it's that file. It's the file that we want. Right. Now, another command that might be useful is history. So this just prints out a history of all of the commands that you've used. I think for mine, I've set my history to be at most 10,000 lines long. So it only gives me the most recent 10,000 lines. Yours might be a bit different. And something we can do, say, if we want to look at the history of commands that only include, for example, make dir, is we can do history and then this pipe symbol, grep make dir. And what this does is it prints out only the lines of history where I used make dir. So this straight bar character here, we usually call that pipe. And what it does is it takes the output of the command on the left and passes it as an input to the command on the right. So the output of history, if you remember, was just this giant blob of text. And grep finds all of the lines in that input that contain make dir. Cool. So as it says here, this is only sort of like a basic intro to the Unix command line. There are many commands out there, but these are probably the most common ones and the ones you'll use the most. If you are interested in any of these commands or you want to learn a bit more, most commands will let you pass --help as an argument, and they'll spit out basically a giant blob of documentation, and it gives you sort of all of the arguments that you can use with ls. So we looked at -a, but there are a whole lot more commands that you can pass through. So if we, for example, look at grep, we can do grep --help, and we get back basically like a help page on how to use grep. The other option is to look at the manual page or the documentation page for a command. You use man, so man stands for manual. And if we just pass it the name of a command, like ls, for example, it'll give us back a page of documentation that you can read through. Cool. That's the end of the Unix command section. All right, now we're going to get a bit of practice working with Git and GitHub, which you will need to do for your assignments and for big homework. So we're just going to start off by creating a repository on GitHub and just playing around with it on the command line. So just head to github.com. Just expand this. And to create a new repository, just click on the green new button here. We don't need to, so we're going to start fresh, so we don't need a template. Give your repository a name. So let's say in this case, so prac C test, for example. You can give it a description if you wish, and then you can make it either public or private. So for your assignments and for big homework, you'll want to leave them private while you're working on them, so other students can't see them. And then I believe after the semester, you're welcome to make them public if you wish. For this one, I'm just going to leave it private. You can also add a README file, so basically a file that provides a description of your project and maybe some instructions for other people on how to use your project. A git ignore file, basically a list of files that you want Git to ignore, so and not commit to your repository. So for example, if you're working in a language where some temporary files are created, when you compile it, you might not want those files to appear on the repository. Or if you have like environment variables or like secrets or other like sensitive information, you don't want those to appear in the repository as well. For now, we're just going to stick to the default Julia template. And then lastly, a license. So it says here, it just tells other people what they can and can't do with your code. Usually for open source projects, it'll be one of the top three. For now, I'm just going to choose the MIT license. And then just click on create repository. All right, so the repository has been created, and it starts off, you start off with one commit, which is just the initial commit. And you can see we start off with the .gitignore file. If you click into it, you'll see the template here. So this was the template for Julia projects. We can head back to the main repository by clicking that blue link. License here, which is the one we chose, so the MIT license, and then the README, which is currently just blank. So to work with this repository and to sort of add changes and play around with it, we need to get a copy or a clone of it and get a copy of it on our local machine. So the way we do that is if you click on this green code button, where you'll have one of two choices usually. So if you've already set up SSH, you can just copy this link. If you haven't yet, you can use HTTPS for now, but I'm going to stick with SSH. So just copy that link and then go back to your terminal. So, all right, we're going to CD back to prac-C work. And in here, we're going to clone that repository. We're going to get a copy of it and put it on our local machine. So git clone, and then just the URL, or that URL that you copied from from back here. And then if you click enter, you'll see cloning. And by default, the directory that it clones into, so the directory that it creates, is just going to be named the same as whatever that repository is named. You can change that by adding another argument to git clone here. So if I name this like test123, for example, you'll see it says cloning into test123. And if I ls, you'll see it's cloned, it's created a copy of that repository, but it's just given it a different name. So I'm just going to remove that one for now. And head into this one. So cd prac c test123. And you'll see here we have license and readme, which are the files that pop up in this repository. Now you'll notice that we don't see the git ignore file here. And that's because, as we said before, any files that start with a dot are hidden files. And to see them, we need to add -a to ls. So ls -a, and we will see the git ignore file. You'll also see this .git file, which .git directory, which basically just gives or provides metadata about the repository, and you shouldn't need to mess around with that. So we can just ignore that for now. Right, now we've got the repository on our local machine. If we run git status, it'll give us the status of the current repository. So we're on branch main. We're up to date with the remote. So we're in sync with the repository that's living on GitHub. And we have nothing to commit because we haven't made any changes yet. So let's start by making some changes. So we're going to create a src or source directory using make dir. Use ls to check that we've made it. Now run code dot. So again, code is VS Code, and then dot runs VS Code in your current directory. So if I run VS Code, you'll see it pops up in the directory in this repository that we just made. And it's got the source folder that we just made as well. If VS Code is not in your search path, so what that means is if you type in code and the terminal just gives you like a command not found error, you can just open up VS Code normally and go to File and open Workspace and just navigate to that workspace manually. Right, so we're just going to start off by creating a basic hello file in source. And we'll just add in a simple hello world. Maybe something like this. Now to run this file, you can either press Shift Enter, or you can click this little triangle at the top, and it just it runs this file in the REPL. So if you click Run, there we go. So it's printed hello world and those 10 numbers that I added at the end there. And again, remember, if you make changes to this document, the white circle will pop up and just telling you that you have unsaved changes. If you press Control S, that circle should go away, which means that all of your changes have been saved. All right, so now heading back to the terminal, we can run git status again, and we'll see something pops up. So it's telling us that we have untracked files. So at this point, Git doesn't know about the changes that we've made yet, hence why they're untracked. So to let Git know about them, or to let Git track them, we use git add. as it tells us here. So if we git add source/hello.jl and then run git status again, you'll see that it changes to this line. So it says changes to be committed, and it lists all of the files that are to be committed. So at this point, we've let Git know that we've created a new file, and we want to include that in our next commit. So at this point, nothing has been committed yet. We've only told Git what we want to commit. So to just commit this file, we can run git commit. And then if you do git commit -m, the string that follows m is the message that you commit with. So what I mean is, for example, if you go back here, this initial commit that was created for us has this message initial commit. So to give this commit a message, we can just do git commit -m and then the string that we want, the message that we want to commit it with. So if we git commit -m hello, if you set up SSH, you'll probably need to type in your password there. And you can see now it says one file changed for insertions, because the file we had 4 lines. And if you run git status, you'll see that our changes have been committed. Now it says your branch is ahead of origin main by 1 commit. So origin main is basically this remote repository that lives on GitHub. And it's this current branch, the one that's sitting on our local machine, is ahead because we've made a commit, but it hasn't been reflected in the GitHub repository yet. So if you run git log, this will give you a log of all of the commits you've made. So you can see this initial commit was made when we created that repository, and this commit here was what we just did when we added this Julia file. Now this commit has not been pushed to the remote repository yet, so that's why it's telling us that we're ahead by 1 commit. So the next thing we'll want to do is push our changes, push this change to the remote file so that it shows up on GitHub as well. So the way we do that, once you've committed, is you just run git push. Cool. It's a bunch of text here, but basically it's telling us that we've pushed to this repository. And if we go and refresh this page, you'll see now we have 2 commits. The latest one was a minute ago, and it was the commit that we just pushed. So if you click on this button here, you'll see basically a git log, all of the commits that we've made. And if we click on hello, you'll see this is the one changed file with the 4 lines that we added just before. To get back to the repository, just click on code. And that's it. So if we head back to the shell and type in git status, you'll see now it says we're up to date, because we've pushed that commit to the remote repository. So now the 2 are in sync. All right. And that's the end of the Git and GitHub section.
Hi everyone. Today we're going to be looking at the debugging section of Practical C. So in order to complete this practical, you'll need to have the Visual Studio Code Julia extension. So if you don't have that installed already, you can come over here in the sidebar to extensions. And in there you can search, I'll just search Julia. And this is the one that you want to have installed, that you'll see pop up. So get that installed and then let's begin. So we're going to be looking at the debugger built into VS Code today, and we're going to be testing it with this little script, which is meant to figure out the probability of a bunch of events happening using the law of inclusion-exclusion. And this is something that you're probably familiar with. If we have two events, then the probability that A or B occurs, so A union B, is the probability of A plus B minus the probability of both of them happening. And if we assume that A and B are independent, then the probability of their intersection is just going to be all of the probabilities multiplied together. This can get a bit complicated when we've got more than two events though. So we want to try and write some code to automate that for us. Now we've got this script to start off with, and we'll take a look at what it's trying to do in a second. But first, let's just compute an example by ourselves. So looking at 1 down here, we've got 3 events with probabilities 0.1, 0.25, and 0.5. So I'll open up my terminal down here, type Julia, so we can use this for calculations. And the way that we'll approach this is first treat the 2 events as grouped together. So we'll look at A1 union A2 as its own event, apply the law of inclusion-exclusion, and then add in the 3rd event. So I'll create a variable P1, which will represent the probability of A1 union A2. Now that's going to be using the law 0.1 plus 0.25 minus their intersection, which is 0.1 times 0.25. So that gives us this number, 0.325, with a bit of floating point error. Now let's add in that 3rd event. So grouping A1 and A2 together, now we're going to add in A3. So we've grouped A1 union A2, that probability to be P1. Now let's do the same law, but using this 0.5 probability. So we'll have P1 plus 0.5 minus P1 times 0.5, which gives us 0.6625. So that's the probability that we should expect for A1 union A2 union A3, all of these events. And that's the example that we're going to be testing this code with. Now let's look at how this code actually tries to approach calculating this number, because we did it by splitting it up and grouping the events. And that's kind of the approach that we want to take in our algorithm as well. So the function takes in a vector of probabilities representing all of the different events, the probabilities for each of them, and we'll assume that they're all mutually independent. So first, we just want to check that there's at least one event. If there is at least one, then we just return the probability of that. If there's exactly one, we just return the probability of that event, because there's only one thing. We don't need to apply inclusion-exclusion. The real interesting thing happens when we have more than one event. So in that case, we want to try this divide and conquer strategy that we already saw when we computed the example ourselves. So we're going to break the list down into 2 subsets, and we're going to try and split it roughly evenly. So we want to take the first half and the second half. We'll compute those probabilities independently and then use inclusion-exclusion to combine them. So the way that we split the list in half is we'll first figure out the midway point, then we take 1 up to that point and that point to the end. And then what we want to do is figure out the probabilities for each half separately. So then we call our function recursively on each of those halves. So eventually this will split the list down until we get to just passing the functional list with 1 element, and then we actually return that probability. Now, what do we do with these probabilities for P and Q? Well, we apply the law of inclusion-exclusion, we add them together and subtract their intersection. Okay, so far so good. So we've got an idea of what this algorithm is trying to do. Now let's see if it actually works. So we're going to create a new file. So over here, I'm going to do that with this little button in the Explorer window. So I'll create a new file and we'll call it inclusion exclusion.jl. Okay, and into this file, let's paste this function. I'm not going to bring the doc string, just the function. And now that we've got this, we can try running it with the Julia extension. So the way you do that is by pressing Shift Enter. Now, if you try to press Shift Enter on just this last line, you'll see that you get an error. Inclusion exclusion is not defined. That's because the way that the Julia extension runs code is it looks at your current code block. So at the moment, it's just trying to run this line by itself. What we need to do is first run this function to define it. So I run that. Now you can see the function is defined. And if I try to run this, hopefully everything should work, but we get an error. So there's a bug in our code somewhere. We were expecting to get 0.6625, but we've got this Stack Overflow error. So that's a bit of a problem. Let's go back to the track. All right. We get the Stack Overflow error. Now, if you see an error which you're not familiar with, a good way to try and figure out where it's coming from is to use the help menu. So let's go down to this terminal again. I'm going to type a question mark to enter the help prompt, and then let's enter the name of that Stack Overflow error. So Stack Overflow, if I type tab, it will autocomplete. And let's get some information about it. So it tells us the function call grew beyond the size of the call stack. This usually happens when a call recurses infinitely. So even if you don't know what the call stack is, it's given us a good hint here that it probably happened because our function keeps calling itself infinitely. We've got some sort of infinite recursion loop going on. So we want to use the debugger to try and figure out exactly what's going wrong in our code. And the reason the debugger is so good is because it lets us step through the code line by line and look at what's happening at each step. Now, let's go back to this file, and we're going to come up here to the menu. We're going to go to the Run menu and press Start Debugging. So this will start the VS Code debugger, and it'll run it. Now, it's stepped through our code, and it's encountered the same error. Let me just close this Julia. Okay, so we've encountered the same error, which isn't very useful, and now the debugger is kind of broken. You can't do much with it once it's run through and encountered an error. We're going to have to restart it. Also, to run the debugger, you can press F5 on your keyboard. That will do the same thing. Okay, so that was no good. What we need to do when using the debugger is set some points where we want it to pause in our code. So we can use that by setting a breakpoint. Looking at our function, let's maybe set a breakpoint before this line, before m equals half the length of p. Now, there's a few ways you can do this. You can go up to Run again and go Toggle Breakpoint in your menu. And you'll see that it adds this little red dot over here. You can also toggle a breakpoint by hitting F9 on your keyboard. Or with your mouse, you can come over here to the side and click the red dot, and that'll add a breakpoint on the appropriate line. So those shortcuts are really good to know, so you don't have to go into the menu each time. Awesome. Now let's try restarting the debugger. So we're going to stop the current one. And let me kill it down here. So sometimes it gets stuck. You'll need to delete the instance of the terminal. Let's run it again. So I can press this Run and Debug here. Okay, and now we can see that it's paused on this line where we've set our breakpoint. It's highlighted that line in yellow. And you can see this is the current cursor of the debugger. So this is the line that it's currently looking at. Now let's come over here to the variables pane. We can see that we've got access to all of the local variables, which are defined in our function. So this P is the input that's being passed into our function. Awesome. Now, let's try and get a bit further into this function. So how do we progress beyond this breakpoint? Well, we can advance, as it says in step 7, we can advance by one line by using the step over functionality. So if we go back to this code, there's a few ways you can step over the line. We can go up into run here, and then you'll see you have all the options here. So step over, step into, step out, continue. We can press step over here, that'll do it. You can also use F10, or you can come up here to this little navigation window. It might be in a different place on your screen. You can drag it around. So come up to the navigation pane, and now we've got all these different buttons. If you hover over them, it'll tell you what they do. So this one is step over. So let's try that. Let's step over this line. So it's gone to the next line. Now, if you look over in our variables pane, you'll see that we've got a new local variable, m. So we've defined m to be 1, which makes sense. That's the integer division of 3, which is the length of our vector, by 2. All right, let's keep going. Let's step over first half. So we get our new variable, first half, 0.1. Everything looks good so far. And second half. Now, this isn't really what we expected. We wanted to get 0.25 to 0.5, but instead we've ended up with the entire array, 0.1, 0.25, and 0.5. That's a problem because now in this line, we're going to be passing that into the function again. But this is exactly what we started with. So we're basically just running the function again with the same input. And you can see that this is going to form an infinite loop. Each time the function is going to call itself with the exact same input. What we wanted when we designed this function was for the inputs to get smaller each time, and eventually they would hit 1. So this is no good. We need to change something. And the problem is in this second half definition. Because Julia's indices are inclusive, we're taking the first element and the last element and everything in between. But you can see our first half also includes the first element and the mth element. So we don't want the mth element to be in both of them. So the way we can fix this is simply by making this m+1. Now, if we change something in the code while the debugger is running, that debugger session is invalidated. So we're going to have to restart the debugger now. So let me do that. I'll restart it. Okay, so we get to this line. Let's step over that. Next line, so we've defined m. Let's keep going through first half. So now you can see our second half is the variables that we want, or the array elements we want, 0.25 and 0.5. We're not including that first one. All right, and we can keep going. It'll step through a few times because of the recursion. And you can see we're finished. So it stepped through and we're done. You can see it doesn't actually print the output value because we haven't assigned this to a local variable. If we want to check our code, we can run it again using the Julia extension. So I'll press Shift Enter. It's waiting to compute. So that's defined the function. And now we get what we expected, 0.6625, which is the same as what we calculated. All right. So that's how you can use the debugging tool in a very basic way to get an understanding of what all the variables in your function are doing. Often you can achieve a similar thing just using print statements, but it's a lot easier to use the debugger because if we had tried to print the second half each time, because we had an infinite loop, our terminal would be spammed with a bunch of output from that print statement. It'd be pretty hard to decipher exactly which one came from which call. And when you have more complicated functions calling each other, it's even worse. So this breakpoint feature is really powerful because it lets you pause the code halfway through and check out the variables that have been defined. Okay, is there anything else we need to look at? All right, so that's covered the practical material, but we should take a quick look at some of the other debugging navigation features. These ones: step over, step into, step out, and continue. So let's go over to this Julia file I've got, which has this little function for adding two strings. So we pass two numbers in string form, it converts them into integers, and then adds them. And let's say we want to understand exactly what's going on in this step of in each step of the code. This is a simple example, but it'll serve our purpose. So I've added two breakpoints before we compute the function. So let me run this in the debugger. Okay, so you can see we've paused at result 1. Now, if I want to run this method without stepping through all of the lines here, I can use the step over method, which is what we saw before. You just step over one line. I can also continue up to the next breakpoint. So that's this button here, F5. So let's try that, continue. That'll skip us straight to the next breakpoint. It will run everything in between. In this case, there wasn't really anything in between, but that's what that does. Now, let's say we want to take a look at the inner workings of this function. Well, then we can use the step into command, which you can see up here is a little down arrow in the navigation pane, or you can hit F11 on your keyboard. What that does is it steps us inside this method. And now we're looking through the body of the function at each line. And you can see over in our variables pane, we've got these local variables A and B, which are the inputs we passed to our function. All right, let's step through line by line. So we've defined X to be 1, 2, 3 as a number, because that's what we passed in as a string. We've converted it to an integer. And by now we might have a good idea of what this function is doing. So we don't care about stepping through the rest of it. We could use the step out functionality, which will run the rest of the function and return us to where we entered. So we stepped into the body of that method and stepped out. Okay, now let's step over. And if we come over here to the global variables, you can see we've got result 1, which is 3, result 2, negative 333, as we would expect. So if you've got a global variable and it's not appearing automatically in your variables pane, it's likely because it's hidden under this global panel. Awesome. So those are some of the basic features of the debugger. It does more complicated things, and you can also customize it using a launch file if you want to make setting it up in a particular configuration quicker. But for basic code, it should be enough to just hit F5 and run through, make sure to set breakpoints on all the lines you want. Okay, I think we'll finish there for today. Hopefully this was helpful.
So, hello everyone. My name's Isaac, and I'll be taking the third part of this tutorial. So we'll be focusing on plotting and how to make nicer plots than what Julia might give you by default, and just making sure plots works for everyone. So hopefully we should have the tutorial sheet up in either iJulia up in Jupyter on your web browser, or you can have it open in VS Code if you want. Either one is fine. And we're up to the plotting section now. So there is a bit of text about the Collatz conjecture, and we'll get to that in a second. But first, I'd just like to make sure everything is working with plots. So VS Code is very nice in that it will show plots in it, but we just want to make sure that Julia has everything that it needs to plot. So we're going to open up our terminal, and we're going to start Julia. And by hitting the close square bracket key, we can get to our package manager, and we need to add plots. I'm not going to run this because it's going to take a bit of time, but this will make sure that plots is installed, that everything's ready for us to go. Also, for Today, we're also going to use plotly.js for just neatening up some of these plots at the end. So add that as well. Hopefully, once you see them, they should have been installed. If you have any issues with that, go on the Ed discussion board. We're more than happy to help with those things. So now that you have it, just to make sure that everything with plots is working before we go on to VS Code, in your terminal, we'll just type using plots to get it like all installed. Note that this does take a bit of time the first time it runs because plots is a very large package and Julia does some optimization on the back end. We're then going to set some sort of X for our plot. So that could just be, say, 1 to 10. We're also going to set the Y or the function that we're going to plot. And I'm going to say we're just going to do X squared. Notice that we have this dot before the power here because X is a list or an array, and we want to do it on each element of that array. So the dot means that we just do the power element wise. So hitting that, we get our nice power squares of X. And to plot, we use the command plot. So first you put the X array of your coordinates, and then you put all your Y coordinates. When we run that, again, the first plot that you make is going to take a bit of time, but we should see something like this where we have our nice quadratic curve X and Y. So just to reiterate, the second time that you plot, it's going to be a bit more quicker, hopefully, to get this plot, and we'll especially see that with VS Code. So if you're having any issues getting the plots up here, go on the Ed discussion board, show what errors you're having, because once it's working here, hopefully it should also work in VS Code, and we'll get that up right now. So back to the practical sheet, we might even do the same thing. So it says that we need to create a new file called collapse.jl. I'll talk about what the collapse conjecture is in a sec, so don't worry. But if we get here and we type the same thing, so we're going to get using plots, we're going to set our X range and our Y, and then we can just plot X, Y. We just want to make sure that everything works when we run it. So run, and hopefully within VS Code itself, we should see some sort of plot for Julia. If you don't see this, again, go to the Ed discussion board because that's really what we want to make sure that everyone can access right now, that everyone does have plotting working first. But we'll go on to the actual tutorial sheet questions. I might just zoom. Hopefully this is big enough for everyone to see. Cool. So the collapse conjecture is an unsolved conjecture that if we take some integer n, and if it is odd, we times it by 3 and add 1. And if it is even, we divide it by 2. And if we keep repeating this process over and over again, it's theorized that we'll always be able to reduce our number back down to 1 just by following this process. So to do this, you can see an example of F6. So because 6 is even, we divide it by 2 initially. Then 3 is odd, so we do 3 times 3 plus 1. We then have 10. So 10 is even, we just divide by 2. 5, odd, times by 3 plus 1. 16, even, divide by 2. 8, even, divide by 2. 4, even, divide by 2. 2 is even, so we divide it again. And we get 1. And once we get to 1, we stop there. And so people have been checking this for many, many n. All the n up to 2 to the power of 68 have all been checked. And everyone that we found has gone to 1, but we don't know for certain whether other n are. So we're not going to show this for higher n, but we are going to just do a little demo to see if we could plot this for the first few n, say up to 100 or so. So we're going to, thankfully, that f function that we have has already been made for us. So we're going to be able to copy over this, including some helper things around, and I'll explain them in a sec. But in your collapse file that you create, we're just going to paste it all in. So the first thing, using plots, means we just have all the tools for plots available. The second bit here is our function f. So first we want to make sure that we have a positive integer. And then the next thing is if our n is even, we're going to divide it by 2. Otherwise, we're going to times it 3 and add 1. And that's exactly what this function is defined here. So we're just implementing that f. We also have our stopping time. So there's a bit of a funny comment here that for large n, say really, really big, no one knows whether it will stop or whether we'll get into a loop that doesn't reach 1. But hopefully, for all the numbers we test, this should end fairly quickly. So we take some integer n, and while n is not 1, we just keep applying this function, incrementing the count by 1 each time, and then we return the count. That will be the number of times we had to call this function. So this function just finds the number of applications we had to do before we got 1. So for this one, we need to apply it 1, 2, 3, 4, 5, 6, 7, 8. So if we did the stopping time of 6, we'd have to apply f 8 times, so we'd get 8 as our response, hopefully. And what we're going to do is, for our x from 1 to 100, we're going to calculate the stopping time as our y, and we're going to plot it. So hopefully, when we run this, these are our x values, and these are how long it took for each of our x values to stop. So you might notice that this is a very jumpy function. It's not continuous. There's lots of different spikes from where we see, say, I think that's about 27. 27 took a long time before it stopped, where something like 28 didn't take as long. So now that we've actually plotted it, we want to make this plot a little bit neater, because this plot here isn't great for if we wanted to present our results. There's no labels on the x and y axes, all those things that you've learned that need to be in plots. We're going to learn how to put them in. So the first thing that we want to make sure that we have is a title, x label, y label, and a legend. So there's a few ways that you can do it. I'll do it first within this plot command. So the first thing we're going to do is title and x label, y label, and the legend, they usually use the term label for that, are all different arguments that we can give. So if we set the title to be something reasonable, so I'm going to, let's say, Collat's conjecture number of steps. And then when we run this, we'll find that we have now a title for our plot. We can do a similar thing for the x labels and y labels. So our x label will be n, and our y label will be something like number of steps. And we can see that those are now our x and y labels. And just a quick formatting tip, when we have lots of arguments in a row, it's sometimes better to display them each on one line. So with Julia, we can now put all our named arguments on a single line just to make it easier to read. You don't have to do this. You can put it on one line, but just to make things nice and easy, we can lay it out so we can see our title, x label, y label, and this is exactly the same thing as before. So the last bit that the tutorial sheet asks us is to change this legend here. So we already have a legend, but it goes off what we call the label, if I can spell. So the label is what it calls this blue line here. So instead of having, say, just y1, we might call this the stopping time. So you can choose your own labels for all this. I might even add Collat's. Yeah. But whatever you feel is appropriate. And then once we run this, we should see our little legend has included that with the blue line. Just going to save that. So that completes option 2 of this. Now, if you do have any difficulties or you want to do something a bit more fancy, if you go to that link on the tutorial sheet, there's a whole page about plots where you can do things like log plots. You can have nice LaTeX legends and labels. I might even show some of that, changing the scatter type. But most of what we're going to do mainly involves just making sure you have X and Y labels, a legend, and a title. So we'll go over a little bit more than that, but that's kind of like the basics that we need. To do something like the LaTeX thing, so that's where you put math into our display, we can do things like L strings, but I'll save that till the very end just so we get the necessary things out of the way. All right. So the next part of our tutorial, instead of plotting the amount of time that it took to stop, we want to record the maximum height or the maximum number that we reached when we did this Collat's conjecture process. So for 6, we got all the way up to 16. So that would be our maximum height. and we're going to write a new function to do that. So I'm going to put the function in here. So this one we want to call maximum height, and it's going to just take our integer n as the input. And now we need to fill in the details of this function. And it's going to be very similar to the last function. So if you want to pause here and see how you would do it, please have a go, because this is the best way to learn. But I'm going to go through the solutions now. So what we're going to do is, the first thing is that we're going to set some sort of maximum, kind of exactly like this loop where we have a count. We're going to set the initial maximum. So initially, we're not going to get ever, like, the maximum as far as we know is n, and then we're going to loop through this procedure and update our maximum as we go. So we're going to initially, our maximum, we think it's n, and then while n is still not equal to 1, so whilst we're still doing this looping procedure and we haven't reached 1, what we're going to do within this while is we're going to do that looping procedure where we set f of n to the previous one, just like we did here. So n, equals f of n. However, we now need to check if this new n is bigger than our maximum. And if it is, we're going to store it as our maximum. So there's two different ways that you can do it. So if this n now is greater than our maximum, we can set our new maximum to be equal to n. And you could also do that in a one-line if statement if you wanted. Another way that we can do this, so I might just comment that out because we won't actually do it this way. Another way that you can do it is just to set the maximum to be equal to the max of n or our current maximum. So in this case, if n is bigger than our current maximum, the maximum will still be set to it. But if n is smaller, our maximum will stay the same. So this is another way. Either of these bits of code will do the same thing. I think this is a little bit cleaner, but it's whatever makes most sense to you. The last thing that we want to do, just like this function, we compute the count. We just need to return it in the end. We've computed the maximum. We just need to make sure we return that maximum value. So we now have a maximum height function. A good thing to just test this is we might just show out what the maximum height of, say, 6 is. So we're hoping that this should be 16 when we run this code. And when we run it, the maximum height of 6 is 16. This just shows out whatever this is and what its result is. So the maximum height of 6, 16. So hopefully it should be working. Let's do a plot to show like an example. So I'm going to set a new y to be the y of maximum heights. And we're going to plot the maximum height on the y-axis and keep n on the x-axis. And just like before, instead of having stopping time, we're going to apply maximum height to each of our x values. So that way we can record it. And then in our plot, instead of just having y, we want the y of our maximum heights. Now, when we run this code, hopefully the plot should change. And what we should notice is instead of number of steps, we're now getting the maximum height that some of these numbers reach to. And this is a very different plot. We have steep peaks at a lot of these numbers, and it gets up into the thousands. So when we do this process, instead of just reaching, say, 16, some of these are reaching numbers above 8,000. So this is just another way that we can see our data. Obviously, you'd want to change also our y and x values for that. So I might copy all of this and keep our old plot, but I'll comment it out. So this one was just with our usual y. For our maximum height, this might be our y-axis is actually our maximum height or the maximum number reached. Our x-axis is still n, and instead of having the collect stopping time, I just might call this maximum height for our legend. So now that we have this new plot, we've just made it a little bit more readable. And instead of steps, we should probably call this maximum height also for our title. So running that again, we get a nice plot, everything's there. So the last thing Oh, okay, lovely. So the last thing that we need to do for this question here is we also want to try different styles of plots. So I got you to install Plotly.js beforehand, and it just allows us to basically have a different style. So Plots has many different backends that it can use. This one tells use the Plotly.js backend, and it will just change the style slightly. So it's easier if I just have a show of this. So we want to using Plotly.js, and what we actually want to do is we just want to call the function Plotly.js right at the beginning. So Plotly.js, and just call it like that. And now hopefully when we run this, it can take a little bit of time. Again, the first time that Julia plots things can take a bit of time, so just wait until it's stopped evaluating things. Be a little bit patient. If things aren't seeming to update, it's just taking time to plot. Within development, they actually call this the first time to plot, and Julia isn't particularly great at this, as it does take a long time to make sure everything's loaded. There we go, finally did. And you might notice that this is just slightly different. The legend is over here. We can change some of those things around. Personally, I'm not as big of a fan, but you might also note that the Plotly.js has like interactive elements where we can find the height of each of them. So that might have been useful before. So that covers a lot of the cheat sheet questions. I'm actually going to turn off these here because they are not, I prefer the usual backend, but whatever backend you prefer, you can do for all your assignments. As long as they're clear and legible plots, we're mainly focusing on how, like, making plots that are readable and easy to use. So I'll just run that again there. Oh, we probably are stuck into Plotly.js. We won't change back right now, but that's okay. I'm just going to show a few other tricks that we can do to help you with your plotting. So if we wanted to plot two things at once, and we just tried to do it by putting the plot first and then the plot second, and we ran this, it's not actually going to show both plots. Because what Julia does is this first plot, it plots it, and then it plots this replacing the previous plot. If we just want to add it on top, we use the exclamation mark, which means basically whenever we see an exclamation mark, it means we're going to edit the previous plot. We're going to change it. And so this means we're going to write over the previous plot. And so now you might be able to see that we actually do have both plots. The blue one is quite small because the stopping time is much, much smaller than the maximum number reached. So just being careful here, this one probably doesn't make the most sense to plot both of them because we can't read much about the other one, but you can plot multiple things at once if you so wish. I'm just going to comment out the second plot and we'll focus back on the one that we did first. So the stopping time. If you see the title label X and Y things, we can also do them later using a similar, so X label, say we didn't want to set the X label immediately, but we thought we might do it later. We can also use X label again with the exclamation mark to say, let's edit that previous plot and put in N. I'm just going to say this changed so that we can see it on the bottom, but I'll get rid of that in a sec. So we can use X label exclamation mark to get that X label to change after we've done it. Similar things we can do with title, exclamation mark, Y label, and those kinds of things. You can also do like the X limits, X limbs, which stands for the X limits. If we just wanted to focus on, say, 25 to 50, we could do 25 to 50. And then when we ran this, we'd just be having this plot where we just go from 25 to 50. So there's lots of different things that you can change here. Feel free to try to work and make your plots pretty. And if you have any difficulties with that, this plots documentation is very, very useful. So it will tell you how to get LaTeX into your plots. So we need to import LaTeX strings, and then you just put L in front of it, and you can get that kind of LaTeX style for all of your plots. You can also do scatter plots by setting the series type. And that's most of the thing. But if you ever have any difficulty with a lot of these things, what you want to look is for the plot and series attributes. So I'm going to look at the series attributes. So all the things like Oh, I'll hopefully be able to find some. But if we had, so our label is a label for the string which appears in the legend. And if we look at our plot attributes, we can also see that we have our plot title, or also known as the title. And we also have in our axis attributes, if we look for it, our limits and our, hopefully, I'm just going to search for this, labels. So if we just scroll through these, we should hopefully find the little text that tells us where. But if you need to look for, say, hey, this is a really good example, and that probably wasn't the best explanation, but say we wanted to change the color of a series, or say change something about our plots, we might be looking for something like our fill color then. And you can go through these properties and find all those different things that you want. So say we wanted to change the line color, we'll go back to our plot. We can just add our line color and make sure, because we are going off the spelling here, it can have an OUR, or we can drop it out. Either one will work. And we just set what it sets it to. So we can use an integer, a symbol, or other things. So it has some examples here. So we might do a black line, going off their example for using, line color black here. And we can see now that our plot has a black line. We could also change it to red if we so wished. And we get a red line on our plot. We can also change, say, markers at each of our points. So we could do, say, marker shape circle. And then at each of the points, we'll get a circle. And we can change everything about the marker color and that. So if you look, especially on the series and plot attributes, for what you want to be changing, you can change all these different properties and they'll explain how all of that works. Another really important one that you might want to do is something like your series type. So that can be like a histogram, or if you're doing a scatter graph, all these kinds of things are contained here, where you can control what kind of graph you actually want, instead of just like having a single graph, but you having the default graph shape. So going back, that's pretty much all I wanted to show you about doing graphs. It does take a little bit of effort to make nice graphs. You probably wouldn't want something like this. We might change the line color back to blue and see that this makes a lot more sense. I don't actually think that we should have our markers on here, and we get a nice plot. Maybe, if anything, we should change this to, what do they say for the line color? We can set it so our line style, we can set that to be different as well. So that's what I'm looking for. So instead of that, we can set our line style to something like dashed, and therefore our plot is a little bit more, dash, sorry, not dashed. And therefore our plot is a little bit more readable, or whatever you think is best for your plots. You have lots of control over these, and you can plot multiple things together or change all these properties to make it look good to what you're thinking. I think that's all that we want to cover. If you have any issues, go see the ed. I know that it would be much better to have this tutorial in person. I can help things with like big homework and any issues that you have. But please, we'll be checking the ed board a lot. So have a go at this. Have a go yourself. You might have seen me do it. It's really good to get there and make sure it works on your system and that you know all the little details, and make a plot that like you would be happy with putting on your big homework, that kind of style of plot. Okay.